Good afternoon,
Good afternoon.
seekers of knowledge. One of these glasses on for us. Okay, let's see how good audience retention is again. 2 tries. All right. Wow, first time. Well done. Excellent audience retention. Wasn't that a great show, by the way?
Yeah.
Loved it. I really did. All right, we're going to talk about the discovery of radiation today. A few days ago, Billy actually mentioned this on the Wake Show. For those of you who are up early and study the Wake Show, you'll see the date in a minute because we've just passed the anniversary of the discovery of X-rays. So that's what we're going to talk about first, X-rays. You're all familiar with X-rays. I doubt there's somebody in here who hasn't had an X-ray, but just out of interest, is there anybody here that's never had an X-ray? Anybody? No, we've all had X-rays, haven't we? You know, we just take it as a matter of course, especially in the dentist office as well. Well, it was on the 8th of November in 1895 that this discovery was made, and I want to try and get you to think about the context of the way this discovery was made. We're all familiar with what it is. We're all familiar with what laboratories are today. You can think of those sterile environments with their benches and all the equipment that's there. But get away from that thinking, because these early experimenters were doing things in, well, in some cases it was the room in their house they were doing things with. They didn't know what they were doing. They were somewhat disorganized in their layout sometimes. And I want you to get into that frame of mind to try and appreciate what Röntgen found. So he was looking at it. He started to do lots of work. Did lots of work alone for many weeks, and he did find out the origin of these X-rays. It was coming from the end of his tube, the Hitov tube, and they seemed to be emanating from the glass itself. He's not quite sure why at this point. Well, 28th of December, which you see there, he gives his paper to the society in Würzburg, and it caused an amazing stir in the science community at that time. He included a photograph of his hands. Can you imagine that he had held his hands in an X-ray beam for between 3 and 10 minutes to get a picture? Nobody in their right mind would do that, today anyway. But then of course the X-rays would be much weaker coming from his tube than what we're capable of generating today. Look at that figure on the bottom bullet. Over 1,000 papers were published on X-rays in 1896. That's the year after he made the discoveries. You can imagine how many people started to play with this new technology. And of course, for this amazing discovery, he did receive the Nobel Prize in 1901. So there you go, the discovery of X-rays done almost in a backroom laboratory by accident. This is an early picture of people experimenting with X-rays. Let me walk you through this picture. The tube that is generating the X-rays is here. There is a fluorescent screen that this man is looking through, and there's his hand right next to the X-ray generation. Down below, we have another man holding his hand on a photographic film. The power supply for this tube is back here somewhere. That whole big apparatus there is generating the power to generate the X-rays, and they are wearing no protective equipment whatsoever, because they had no idea what X-rays could do. All right, now we're going to take a step further. We're going to talk about radioactivity. Radioactive elements emit radiation. And it was very soon after Röntgen's discovery of X-rays that we start to discover radioactivity, and this is how it was done. So, Henri Becquerel is credited with the discovery of radioactivity. He hears the work of Röntgen's discovery, and he starts to conject that other things will do this. Other fluorescing materials might do this, because they didn't quite know in the early phases what it was. They thought it was a fluorescence process that was responsible for generating the X-rays. So he tested all kinds of things. He had no success until he tried some uranium. He got hold of some uranium. And how he found this out was also by accident, as it were. So, with a photographic plate that he got sealed in an envelope, he put some uranium compound on it and put it out in the sun, thinking that the sun is going to energize the uranium, and it will be the uranium then that fluoresces this new X-ray out, and he will have discovered that it's coming from this process. Well, he did get the uranium. He did find that, and he thought it was the sunlight that had done it. There had been some process in the uranium compound that had converted the light, the energy from the sun, into the X-rays, which he had now detected on the film. So in the picture here you see the rock lying on the covered film, and then over on the other side you see the shadow on the developed film from the uranium. He repeated this a couple of days later, or a few days later. It was a cloudy day in Paris, so he didn't think this was going to work because this material obviously was not absorbing any sunlight, so there was no point in doing this. So he put everything away. The uranium, the photographic plate, it all went in a drawer. And later, he just went ahead and developed that, and very strangely, he found an intense image. And this is the image here that's behind me on the screen that he found. Well, he couldn't quite understand this because there was no sunlight to activate the material that was on the photographic plate. Then along come the Curies. Marie and Pierre got married, and she was still working in the university at the time. It was actually on the advice of her husband that she started looking at this type of work. So she tried to look at every element to see if anything would behave as uranium did. And she didn't find anything except for thorium. Thorium did the same thing as uranium did, that is, it ionized the air. They could measure a current in some air. She then proposed the word radioactivity to describe this result. And that's where radioactivity comes from. It comes from her work. Any gamers here? Half-Life? Anyone? Yeah, very good. I love Half-Life too. And this is also the symbol for Half-Life that the game took. Those of you who don't know what I'm talking about, just forget this part of the presentation. This is the half-life. So as I said, for every period of time that is equal to the half-life, half of the material goes away. It decays to something else, and this graph shows it. So if we start with a unit amount of the material, in one half-life, which is here, half of it has gone. It is transformed into something else. So there's one half-life. Here's another half-life, so now we've got two half-lives. Half of this is gone, so now we're left with a quarter. And so on, until we get out to 5 half-lives, and you're left with about 3%. Nominally, we say... So, starting with 100 kilos of residue of pitchblende from a mine, they went through this process that's described on this slide, and I want you to try and appreciate what they did. First of all, they had to grind the ore by hand in a mortar and pestle. No liquidizers, no grinders. It's grinding it by hand. So you're doing this over radioactive material. It's quite strongly radioactive. Then they had to dissolve it in various solvents. And none of these solvents are particularly nice. They're acids. They would have to heat it, for which the acid fumes would be coming off. They would have to stir it, which they're still getting exposed to acid fumes, and there are no fume hoods. This is all going into the atmosphere in the room. This slide shows you some of the conditions that they worked in. These huge vats here of material. He's right over it with no respiratory protection whatsoever. And I can't imagine what the air smelt like in this laboratory from all the acid fumes. They did this for 2 years. Non-stop, 2 years, they kept doing this and doing it and doing the chemical separations. And then they discovered that they had something else. They didn't quite know what it was. They were able to determine an atomic weight. They discovered something at around about 174, something that weighed about 174 atomic weight. It's different from barium, which was in there, which is 137. They had not reached yet radium, which is 226. They knew they hadn't got a pure substance, so they kept at it. And after 12 years of doing this, they got a pure sample. Now, he died in 1906. He got run over by a horse and carriage. This is the announcement here. That is the type of horse and carriage that ran him over. It doesn't matter. He was on his way out. He had leukemia, I believe it was, but he had a radiation-induced disease. And indeed, in 1934, Marie also died, and this is almost certainly due to the radiation exposure she received when she was working with this material. And as you see there, after her death, the equipment that she was using, her books, even her cookbooks, were found to be strongly contaminated. So the two of them probably had quite significant radium body burdens, but we don't actually know how much. Why are things radioactive? Why do we have these things to plague us? There's a reason. And the reason is really very simple. If the nucleus is unstable, it's radioactive. And surprisingly, you may not know this, everything above atomic number 83 is inherently unstable. That is polonium up. Everything up is potentially unstable. And things like tungsten, for example, they have looked at tungsten and found some of the isotopes have incredibly long half-lives, so long that you treat them as being stable, but they do actually have radioactive decay occasionally. Here are some of the well-known ones. Technetium here is an unusual one because it is well below that polonium in the periodic table. Technetium has no stable isotopes whatsoever, and it's odd. There's promethium, polonium, that's the killer. Astatine, it's a gas. Radon, you're probably all familiar with radon. You've heard of it, it's a gas. Francium, radium, it is notorious for the radium dial painters. Actinium, thorium, protoactinium, uranium, and curium. Curium is named after Marie Curie, as some of the higher elements that have been discovered are named after famous people. I haven't listed all of the radioactive elements, but just some to show you. Natural radioactivity. I hope everybody knows that there is natural radioactivity all around us. In fact, you are now sitting on radioactive chairs, because some of that material that you're sitting on is radioactive. Carbon-14 will be in the wood, for example. It's naturally radioactive. There are 35 primordial nuclides, and some of them have very, very long half-lives, which is why they're still with us today. Some of them you know well. There's uranium-238 with 1 billion years, as 3 times 1 billion years as a half-life. Potassium-40, also with 1 billion years, and we all contain potassium, so that is why we are all radioactive. Some of them have short half-lives. For example, radium there, 1600 years, and one of the radon isotopes only less than 4 days. You might ask, well, why do we still have them? And that is because they're part of a big decay chain. An example shown there for the uranium-238 decay chain. Then there are 25 cosmogenic radioactive elements, radioactive nuclides, and they're generated in the upper atmosphere from the cosmic rays. So the upper atmosphere is bombarded, there's interaction between the rays from the sun, and they make radioactive materials. Carbon-14 is one of them, and this is how you can do carbon dating, and it's made in the upper atmosphere. So, natural radioactivity, it's all around us. I mentioned potassium-40 is inside. You've got radon coming out of the ground from the uranium decay. You've got the cosmogenic radionuclides made in the atmosphere, tritium, carbon-14, beryllium-7. You've got cosmic radiation impacting on you coming from the sun. And, sorry, that's coming from deep space. That's the sun's radiation there. So it's all around us. If we look back in time, this is a very interesting figure that I found, and I thought it was worth including in this, although it's a little bit outside the discovery. This is the time frame here in billions of years. So that's giga-annum, it's billions of years. This is the radiation dose, the background radiation dose. The unit is in material. So here we are today. This is the background dose today. And as you can see, it's been steadily decreasing since the formation of the planet. The dose has been going down. As we evolve, radiation dose has been higher, which is why we have repair mechanisms, and generally they function very well. You might want to know what's going on there in that strange blip. That is the rearrangement of the mantle as the Earth started to cool and coalesce. And that brings me to the end of the discovery of radiation. And if there are any questions, my wife will run around